like the Damascus Steel. Like, what can you tell me about that?
Sure. So people say there's a lot of debate on the internet, but people say Damascus Steel is a lost process, which is true and not true. It is no different than some other things that we've done contemporarily. The difference is at the time was the input material. Again, none of this is 100% settled, but the best explanations I've seen are it was a steel called WOOTZ, WOOTZ, exported from India that had just the right amount of the right impurities to make it more similar to modern steel, combined with some techniques to bring out the best in it. So, there's been reports of, the right amount of martensite, the, carbon nanotube.
Greg Sheldon here, your host of Metal, Steel, Manufacturing, and Business Pro podcast, where you learn everything about the metals and manufacturing industry that make your modern day life possible. Hello, everybody. Welcome to the show. Due to popular demand, we have Alvaro Mendoza again, AJ, he likes to go by, which is easier for me to say too. So AJ, welcome. Thank you for coming on. And I'm excited to hear about your experience in teaching the kids metallurgy. So
Sure, Greg. Yeah, it's a pleasure to be back. We had such a fun time last time. I wanted to come back on. We were talking briefly before about material science in the schools, and I think it's such an interesting topic because I know before I settled into material science, my freshman year at University of Florida, I had no idea what it was. I picked the name out of a catalog, out of about 25 other disciplines, and it sounded cool. Eventually, I figured out I was in the right place, right? But I think it's such a unique field because it sits kind of at the foundation of chemistry, physics, other engineering disciplines, in kind of a way where you don't really realize it's there until you run into it. And part of that is you don't really see you don't have any exposure into materials principles until you're in college. There are programs aiming to change that. I know ASM, the American Society for Metals, has a materials camp.
Right.
I participated in college. What they do is they actually bring in elementary, middle school, and high school teachers, and they run a camp and run experiments with them and teach them how to bring materials education into their own curriculums, and then send them home with a goodie bag of stuff to run their own experiments with.
Yeah.
That was a fun experience. I was basically the gopher, the university liaison. Hey, we need a Bunsen burner, and I had to go beg, borrow, and steal any kind of equipment they needed to run their experiments.
It's part of the fun, right?
It is part of the fun. I think I surprised them a little bit because we had one of their experiments they run is taking a penny and rolling it, putting it through a rolling mill. It's a common industrial process.
Sure.
And usually they have a hand cranked rolling mill, and not too dissimilar to what you'd see if you put your 2 quarters and a penny in one of those novelty machines, right, to get an imprint.
Yeah.
And the hand cranked mill usually, and I was like, well, we got a rolling mill in the basement that I roll nickel-based superalloys on. Do you guys want to use that? I can run it. So we go down there, and they said normally, they have to crank this mill a bunch of times to bring the penny. It's a 2-high rolling mill, which means that there's 2 rollers, top and bottom. We could have put backing rollers on there, which I sometimes did for superalloys, but we didn't need it for copper. And so I put one of these pennies through and turned a penny into about a 10-inch long smear of copper. It was down to a foil, and they were like, again. And so I think I rolled 50 pennies that day.
Yeah. Hey, Matt, question came to mind. Do they still make pennies out of copper?
They're clad in copper.
Clad in copper?
Yeah, they haven't been full copper for years. In fact, they were steel during World War II. There was a rash of steel pennies out there.
Yeah.
collector's items.
Crazy. So you guys still have pennies in the US, yeah?
Yeah, I mean, I don't know why. I think there's a
We don't here. We got rid of them. The biggest thing you can, or smallest thing you can use is 5 cents.
it would certainly make a lot more sense, but there's a lot of reticence.
Uh-huh. Yeah,
I
I'm
mean,
still not sure about it. You know what I mean? Because it doesn't really
I
evenly.
think it's one of those things where like it doesn't the penny doesn't interact with anything except people's hands, and then ends up in jars or couch cushions somewhere.
True. True. Yeah. And I think it's just a push towards everything digital, which is fine. But anyway, sorry to interrupt you.
It's all materials, right? No, so I mean that was my first. I was like one of the experiences where I saw, I was already in college and grad school at that point, and started thinking about, well, why don't we learn some of this stuff early on? I mean, so many people go through life having no idea about the materials they interact with on a daily basis.
Mhm.
Um, you know, why we use copper for wiring, why cast iron for for cooking pans, or
Yeah.
aluminum, or whatever. Why use steel for nearly everything, or
Yeah. Yeah.
aluminum for specific things. And that's just the metals. You have a whole nother discussion on
Well,
plastics and ceramics, electronic materials.
yeah.
You know,
Look at it
even
started
for
with,
something,
sorry.
that doesn't, that outwardly doesn't look too different, like our phones, right? From the first generation to now of phones, the insides changed so much. The glass technology, the innards, even the materials made out of the back of the first iPhone was a magnesium alloy for weight. This is a little known fact. Apple bought the sole U.S. rights to a company called Liquid Metals, a bulk metallic glass, and they were using it. They never ended up using it in a phone, but what they did do is they made the little SIM ejectors out of it to test it out.
Oh, really?
So for a while, these SIM ejectors were made out of a bulk metallic glass called liquid metal. I never went anywhere, but they were investigating it for other things.
That's interesting. Thanks for sharing.
This kind of little facts interest me, so I end up collecting them.
It is interesting, and I'll just say that, that's neat. So teaching the kids. So you were saying before we get on, that you're discovering that the learning process is interesting, and you guys all you share the same book, but there's different, people are learning at different paces. Yeah.
So the book, William Callister's, I forget the exact title. It's the material science intro textbook. And the intro material science class I find is an interesting one because it's mandated by nearly all engineering disciplines. But at least, but the professors don't always, usually they're from the material science faculty. If there is faculty, if not, they're a mechanical professor, some other who, can teach it. And, it's really interesting because I find that the way it's taught has such an effect on the students' enjoyment, because I'll be honest, the beginning of these textbooks is really tough because you jump right into chemistry. You jump right into electron configurations and what's going on at the atomic level, which isn't the most exciting, and then isn't really, it's really tough to connect to. Well, why am I thought I was finished with chemistry. Why am I learning this? How do I apply this to the rest of it? And what's not really explained well, I find, is that what they're trying to do is build the foundation up to understanding materials on a macro level. It starts at the atomic level, and then we get to the micro level and all that. But there's not always a great grounding of these this education in applications. I was tremendously fortunate to have the teacher I did. Dr. John Ambrose was a very tough teacher. He'd be the first to tell you, and be proud of it. But in his in his spare time, his off days, he was a professional engineer who testified, in various court cases. So in between, in lectures, points would be punctuated by an example from a court case or some investigation he did. So you don't always see that, and I find that it's really tough for people to, especially when what you're trying to do is connect people to a subject like materials where they've never thought about it before, they've never run into it before. How you connect that to what I'm learning in the class? How do I connect these equations that I'm supposed to learn and use on a test to the properties and stuff that I want to be able to use in my professional life?
Mm-hmm. Mm-hmm. So in your tutoring that you're doing, what are you finding out with your students would be a good way to, is it smaller steps and start them off with something they're interested in and then move them into that, or like what do you discover?
I think when you're teaching, it's always about connecting with your students, with the people who are you're trying to teach, right? Whether that's a college student like those I tutor, or whether that's my professional audiences who I'm trying to connect what I'm telling them to their jobs and why they should care, why they should know it. I think it's always about connection. It's about one of my students is got interested in knife making, watched Forged in Fire or something. You hear that all the time nowadays, right? And so we talk about steels a lot, and you can relate it back to stuff he's done hands-on. Another is very interested in aerospace and airplanes. Well, I have some experience there, so we talk about why you would need why would you use aluminum for the fuselage and steel for the landing gear, right? And then the processing that on those different materials to get to that point. So it's all about connection, and that's a tough thing it's an easy thing to say, it's a tough thing to actually do. But I think it's worthwhile. I think that's what really hammers the point home. And sometimes it's on the students too. You got to find, hey, what about this interests me, and then delve into that.
Yeah, absolutely. Yeah, and then that's part of the process for them, right? Is just going through the education process, like any of us. You don't truly know what you're interested in until you at least experience something. So it's just forging a path forward.
My intro to metals class was the class that solidified my desire to be a metallurgist, right? I took the intro to materials and was like, this is pretty cool, I like this. But intro to metals was like, oh yeah, this is where I want to be. And then through that got to nickel-based superalloys, my specialty, and said, no, this is really where I want to be. And that's what I did.
Yeah.
But it's all about charting your own path. Whether in life and business and school, whatever it is.
Yeah, it is, man. Absolutely. So what, I know I was just doing a video about this the other day. Like for me, metals, like it's almost like a genetic memory or something. Like it's in my blood. Like I just love it. I don't know why.
Yeah.
There's something about, it all started with Lego for me, but then somehow it morphed into metals. Like it was my first experience with metals was just like, oh, this is where I'm supposed to be at. I didn't go down the path you went down, but it doesn't change my interest level. And
no, absolutely not.
Wondering, like for you, was it a feeling, or was it what?
Yeah, it was. It's one of those things. The class just kind of clicked, right? I had an outstanding professor. He ended up being my thesis advisor, and Dr. Gerhard Fuchs at the University of Florida. And he taught intro metals and a lot of metals curriculum I took, and he's a fantastic teacher. But it also kind of just clicked, right? It made sense. Learning can sometimes be a chore, and school can sometimes be difficult, even if you do like the material. But it was easier because I did enjoy it, and I still geek out about it to this day, right? That hasn't changed. But yeah, Legos is a big one for me as well. And actually thinking back on it, I played lacrosse as a kid, and
Right.
all of the the shafts for the sticks are metal. Um, and they had all these cool names, ultra alloy. It's this gold thing, gold shaft. And looking up later, I was like, it's all 7075 aluminum, all of it.
Right.
It's all like the same 2 or 3 alloys.
Yeah.
But it was so cool. And then the first time I got a titanium shaft, it was like, oh my god, this is so light, it's so thin.
Yeah. Yeah, man. I
You look back in your memory, it's like, no, I should have known. I should have known better.
well, yeah. Well, but I mean, you don't, right? And that's same with me. Aluminum always fascinated me so much because a lot of toys were made out of it. And like I remember one of my first like metal experiences as a kid was forming the transom on my tin boat, where I was, hammering it. I had no idea what I was doing, but I just felt good about it. It was like, oh man, this is what I should be doing. So
Yeah, exactly. It's responding the way you want it to, and it's doing the things you want to,
Yeah.
and you're doing it with your hands.
Yeah, I regret. Well, I shouldn't regret. I mean, I still got lots of time to use an English wheel, but I haven't gone down that path yet to do that with a piece of aluminum. So anyway,
Well, that's an old process, burnishing, right?
well,
That's
true, but sometimes it was the best,
Oh, absolutely, yeah. No, it's a it's a it's really cool to see which techniques have evolved and grown. I'll be honest. I heard a talk from a guy who, if I had known this was a possibility when I was a kid, this would be my ideal job. I'll settle for being a regular metallurgist now, but there's a guy in the UK. He's a famous archaeometallurgist. In the 60s, he got a job at the British Museum. And since then, he's been studying, arms and armor and all the stuff from the Middle Ages and the Renaissance and all that. But through the vein of metallurgy. So, there's metallurgy papers out there talking about, Damascus steel and, what made, this armor stronger than this one or whatever. So that would probably be my ideal job if I could go back and do it again, but I'm pretty happy now.
Well, that's good, man. So how much do you know about that stuff? Can I ask you a bunch of questions about the history of some metals?
Yeah, absolutely. I'll tell you what I can. If I don't know, I won't make it up.
Okay, well that's good. I don't want to put you on the spot, but I'm curious. Like the Damascus Steel, like what can you tell me about that?
Sure. So people say there's a lot of debate on the internet, but people say Damascus Steel is a lost process, which is true and not true. It is no different than some other things that we've done contemporarily. The difference is at the time was the input material. Again, none of this is 100% settled, but the best explanations I've seen are it was a steel called Wootz, WOOTZ, exported from India that had just the right amount of the right impurities to make it more similar to modern steel, combined with some techniques to bring out the best in it. So, there's been reports of, the right amount of martensite, the, carbon nanotubes in the steel. There's all kinds of stuff out there, but the process kind of died out because the input material was gone. It was used, a specific vein was used up, or whatever it is. But it's one of the most famous, but it's not the only special steel out there. I mean, near the same time, Europeans were doing what's called crucible steel, which is similar to what we do now in principle at least, and making very good steel into arms and armor. That is it's all about reducing impurities, right? Keeping your carbon content in the right place, reducing impurities, or keeping the right impurities there.
So how did they do that, when they didn't have the technology we do now?
Well, I mean, it's the steelmaking process hasn't changed, right? It's in the development of materials. It's it's fascinating what appears when. In fact, I encourage you to go to there's a heat treatment company called Bodycoat,
Okay.
Bodycote, Bodycoat, and they have this great interactive history of metals thing on their website.
Okay.
It's a great, it's well done, well researched, and a great resource. Very
Right.
cool to look at. But they talk about copper, steel, and all these other materials, and kind of when they came about. And everything happened earlier than you think. Copper is the first material to be used, first metal to be used as we would think about it, because it's what's called a native metal. It's found as metallic copper in the ground. You can dig up a chunk of copper, right? No processing necessary. Beat it against a rock. You can hammer it into a shape, right? There you go.
Right.
So it's the first to be formed, first to be melted, first to be cast, all those things,
Okay.
because we didn't require any processing. Iron requires processing. We started with cast irons, pig irons, and over time, you reduce the carbon content, get down to a more usable steel, and then then you're modifying the carbon content, right, to do different things. And then we don't really have a great way to control impurities besides burning them off.
Right.
But
What would those different things be with the carbon content, like hardness and those sorts of things, malleability?
hardenability. So hardenability, hardness, toughness. The kind of steel you use for a kitchen knife is different than the kind of steel you use for a machete, right? One, you want to be able to beat on I'm trying to hack back a forest or something. I wanted a tough blade that maybe takes a bit of an edge. For a kitchen knife, I want something that's super sharp and will stay sharp for a long time.
Right.
With a very thin edge. It's material selection, right?
Yeah.
Which is a big foundation of material science nowadays.
Sure.
But it's the same thing.
So when it comes to stainless, you've got the different types of stainless, right? We've got, austenitic, martensitic, there's another ferritic.
Yeah.
And then, so if you can explain the difference between those, but also I'm wondering about the classifications. So you've got the 300 series and then you've got the 400 series. What are the differences? And
sure.
Yeah. If you don't
well,
mind.
the great things about steel, as when compared to other alloy groups, is things like nickel superalloys, where I'm from, right? The names make very little sense in terms of what they are. They are all developed by they're all proprietary alloys. At least it started that way. Developed by specific companies who have their own naming conventions, and one or the other, the names make very little sense. Steels, on the other hand, since they've been in use so long, have a pretty great classification system. So different countries have their own. I'll talk about the generally recognized SAE, the Society of Automotive Engineers, and the AISI, American Iron and Steel Institute classifications, because they're the ones I know best. I know a bunch of other groups have their own, but for steels, you have carbon steel, right? Let's talk about carbon steel. That's iron and carbon only, right? You've probably heard low carbon steel, medium carbon steel, high carbon steel. That's really just, like it says in the tin, it's the amount of carbon. Low carbon is up to about 0.25% carbon. Medium is about 0.3 to 0.5. High carbon, 0.6 to 1% steel carbon. And then, low alloy steel is where you have up to about 10% alloying additions. So that's kind of general classifications. But within that, you might see a 4-number designation, right? 1095, 4140, right? Those mean something. The last 2 digits are the carbon content. So 1095 is 0.95% carbon. 4140 is 0.4% carbon. The first number, so the 1 or the 4 in our two examples, is the general category. 1 is all carbon steels. That's that's carbon and iron. Some other examples: the 4,000 are moly steels. The 7,000 tungsten steels. This is all kind of information that's very readily available. Sure. Wikipedia is a great table. You can go on nearly any steel making site, and they'll have their own kind of explanation.
Yeah.
So the second digit from the left, so the 0 in 1095 is a more specific designation. So within the 1000 series, you have carbon steels, manganese steels, nickel steels, so on and so forth. So 4140 is a chrome moly steel, and 4340 would be a nickel chrome moly steel.
Okay.
So I don't remember all the stuff off the top of my head. I made myself a little table.
Yeah. That's why we have books and the internet.
Yeah, this is one that actually comes with my some of my courses. So
Nice.
I keep it next to me because it's all the things that I want to hand when I'm talking about some of this stuff: phase diagrams, periodic table, all that kind of thing. So I made for myself, but I thought, hey, people might like this.
Yeah. For anybody just listening, AJ showed us a book that says Mendoza Metallurgy on it. It's a beautiful little book that you can take anywhere. So reach out to him. Where do they find you again, by the way?
MendozAmetallurgy.com, and you can find my email and my business number there.
Cool. Thank you.
Yeah, thank you. So stainless steel grades. So we talked about the different types, right? And so stainless steel as a category is, and this number is kind of, I've seen different numbers, but around greater than 11% chromium. That's what creates a stainless steel, right? Okay. The chromium oxide is what you want forming your protective barrier between the outside world and the steel.
All right. So let me just ask a question.
Yeah.
It's a silly question, but I'm curious. So when I grind stainless,
yeah,
that barrier between the atmosphere and the metal, is that formed back instantly, or is there a time period? Or
not instantly, but it does come back. It forms. It's a reaction that forms in response to chromium being exposed to air, to oxygen, right? In fact, I'm sure everyone has heard of 316 stainless steel, right?
Of course.
Okay, and how about 316L?
Yeah.
Okay, so you want to know the differences?
Well, sure. I think I have an idea, but you go ahead.
Do you know the difference?
I believe it's L is 15% or higher nickel, correct?
But yes, but it also has to do with the carbon content. It's actually low carbon. And the reason for that is it prevents a condition called sensitization. So chrome functions in has two functions in the alloy, right? One, it forms your layer of chromium oxide to prevent corrosion. The second function is it forms chromium carbides, which strengthen your microstructure. A lot of steels are strengthened by big, heavy carbides, moly, tungsten, and the like, forming these carbides that provide strengthening. So the problem comes is that if you have a high enough carbon content, you might preferentially form these carbides over replenishing your chromium oxide. So there were problems where we call the reservoir of chrome in the material to use for reforming your oxide was being tied up in these carbides, and you weren't reforming your oxide layer or forming it too thin or the like. So they made a low carbon variant that lowers the amount of carbon in the material and then makes it more resistant to corrosion because you don't lose it to carbides. So 316, 316L is the difference is corrosion resistance, right?
Okay. Okay. Cool. So where does the chrome, the what's it called? Chromium or chromol or
Chromium.
chromium?
Chromium is the element.
So it is an element. It's on the periodic table.
Cr. It right near nickel and cobalt and iron. They're all kind of in a line.
So is it mined for? Yeah. Or
Yeah.
okay.
Yeah. I mean, they're all mined for.
All
Yeah.
right. All right. Okay. And then aluminum. I mean, I know it creates its own oxidization as well. Certainly, if you've ever welded it, you know that removing that is important.
Right.
You know, so what happens there? Is it the same sort of process where it oxidizes, you know,
Yeah.
relatively quickly, you know?
Yeah. I mean, if you think about the metals that we use every day that have a good oxidation or corrosion response, the reason they do is they form stable, thin, and protective oxide layers. So there's you have a couple different types of oxide layers. You have iron, right, which forms rust, which is flaky, and it falls off. When it does, it exposes the surface for more oxygen. Um, you can have thick, brittle ones. Some of the refractory elements do that. But the ones that we think about in everyday life that form good adherent oxide layers, aluminum, titanium, chrome, are the kind of the three best examples, are used for their corrosion resistance, right? Titanium is fantastically corrosion resistant and used in that application. Same with aluminum, and stainless steels, nickel alloys, which have a lot of chrome. So you're leveraging those oxide layers for protection.
Cool.
Of the environment.
Cool, man. Well, that's interesting. So when it comes to the welding process, I mean, did he talk about a lot of that in metallurgy, welding and
Yeah, I mean, yes. Metallurgy is a wide field that covers every bit of metals from the where it comes from the ground in mining, that's extractive or hydraulic metallurgy, um, metal making, metal forming, welding, corrosion. All these are part of it and can be considered subsets. So there's a lot of people who just specialize in welding, and they're sought after. And
okay.
There's not a lot of metallurgists out there, to be honest. There's not a lot of schools that have dedicated material science departments or even metallurgy departments within that.
Yes.
So
why do you think that is? I mean, it's so interesting, I mean,
it's one is that there's not, it's not we talked about it's not a well-known field, right? So students need to know that it exists to choose it as a major, right? We don't teach it until sophomore, junior year in college, and in which case they're already mechanical or civil, or that's the path they're on, or that's what they want to do, but they you don't know about it till later, and switching majors at that point is tough. In grad school, we do see a lot of people from other majors coming into material science for grad school. I've seen physics, chemistry, mechanical, even computer scientists who come in because computational material science is a big thing, right, nowadays. So it seems to be less of a thing that people choose for undergrad and can become very popular in graduate school.
Yeah.
Even some doctors who go the route of going down the biomaterials route before medical school. I had a friend who did that.
Interesting. Yeah. I mean, material, I would think with all the semiconductors and all of the chip, I mean, all that stuff right now in silicon, material science has got to be, right? And does metal play a part in that?
Yeah, sure. I mean, even I have a couple friends out here in Portland who specialize in metals, and they're working at Intel, right? We all learn material science, and the principles aren't exclusive. For example, the processes that make silicon, silicon for wafers is not too dissimilar from the processes that make single crystal turbine blades for the aerospace industry. They're both single crystals and are two of the most most robust single crystal processes out there, in use every day.
Very interesting. Cool, man. So what can people look forward to in a career in metallurgy? I mean, I would imagine there's so much to see and so much to learn, right?
There is. I mean, like I said, anywhere from working with the mining companies extracting it. I've kind of bounced along more. I've been in aerospace for most of my career. A function of my selection of nickel-based superalloys as a specialty, but also just a genuine desire to be in the aerospace industry. And even then, I'd bounce around from forging and isothermal forging to investment casting to making the metals. So I've seen a little bit of everything. But it's there are not a ton of companies that hire, let's say, just straight metallurgists, right? But there's not a lot of us out there. But where we are is anytime that metals interact with a process, right? Anywhere from even fiberglass making, right? I mean, I've spoken with people like Owens Corning, who they use super alloy type materials in their fiberglass process to make it, and so that requires metallurgy. There's a limited amount in the chips industry, right? But it's definitely any heavy manufacturing process. Metals are involved there, and it's interesting. A lot. There are. I'll speak to aerospace specifically because that's where I have a lot of experience, and I've worked mostly in the supply chain. You have to understand the way modern aerospace companies are set up. So a lot of people would say, well, what about a company like Boeing or Airbus? And I believe there are metallurgists there. I have some friends who did metallurgy and then are doing other things there. But those kind of companies, what they're designing the plane, right? So what they're doing is, they design the whole bit of the plane and then send it out to their supply chain. Some is made in house, but it's all assembled in house, right? And that may go out to, for engines where I have a lot of experience, it goes out to what are called the primes. So if you're on an airplane, commercial one at least, chances are it's going to be either a General Electric, Rolls-Royce, or Pratt & Whitney engine on it, right? Those are the three big ones. And under them, there is a whole supply chain providing all of the parts for that. Again, some parts are made in house. It flows from the designers at those companies who design the parts, the dimensions, the alloys used, mandate heat treatments and all the like, and create a specification which flows down to their suppliers, which is kind of where I came in. I was at first in the forging industry and then casting, working at a supplier, making parts directly for those engines. And these companies are big companies, a little bit vertically integrated. There are a couple different ones. Precision Cast Parts, where I worked. ATI is another one. Alcoa, Arconic, Howmet Aerospace, whichever they are nowadays. Yeah. They have a forging division, they have a casting division, they have a fasteners division, they have an aerostructures division, they have there's only a limited amount of companies that you don't need you don't need a ton of companies out there doing stuff for a relatively small market. I mean, aerospace is always increasing, but it's not like the amount of cars on the road compared to the amount of planes in the sky, right?
Yeah, definitely. Or cell phones or whatever. Yeah.
Right. And then then the regulations, right? Aerospace is for very good reasons very heavily regulated. In fact, it's surprising when I deal with other industries. Um,
In comparison,
the
yeah.
in comparison, right? I'm used to rigid quality standards, inspections, and these kind of things. And then sometimes it feels like the Wild West. But if you're making a commercial part or consumer good, it's
Yeah.
the strength of the steel you make a phone casing out of is not hypercritical.
Yeah, I
It's
think that was one of sorry to interrupt you. I just was going to say, I think that's one of the biggest things I learned going into the trade coming from school was learning where it's important to be tolerant and not tolerant,
yeah,
on your
yeah, yeah.
dimensions, like what's important because the economics of it come into play, right? And I didn't understand that coming out of school until I'd been in the trade for, 5-10 years, you know. So that's something to think about, right, for people.
And it's something that's generally not taught to engineers. I'd be honest, I've had a couple of good role models who have taken time out of class or from work or whatever to sit down and really explain, this is why we're doing these things, this is why it's important. Sometimes it is silly, large businesses can do silly things for silly reasons, things that feel short-sighted or the like. But in the engineers aren't don't come out of school understanding the things they need to do, because they're taking these technical classes and been testing on it. Honestly, the two, every engineer should have a technical foundation in what they're the kind of engineer they're trying to be. But honestly, in my experience, the things that are most important um, are soft skills, the ability to present your work to a boss, to a colleague, to management, to talk to operators on the floor, or customers or people in other departments who maybe don't know what you do. Use of Microsoft Office, Excel, and stuff. You're an engineer, at least in my experience, when you can make a pivot table and understand what you're doing. That's kind of one of the the whole. There's so much data processing that it becomes super important. But and we put engineers in interesting positions because, at least for me, it felt like I was in a very unique spot, because a lot of in aerospace, a lot of engineers have a lot of responsibility for their parts, for their processes, and the staff on the floor sometimes look to us like we have the answers, like I can affect a lot of change. And then I'll go to management and try and do that, and
Mm-hmm.
You feel like you're kind of in the middle, troubleshooting things and trying to solve problems,
Mm-hmm.
and it can become difficult to solve those problems, right? And we in engineering school, right, you're taught how to solve these problems, right? How to do problem solving to work the problems themselves, but we don't learn a lot about the process of dealing with people to solve these problems.
Yeah.
And that's kind of a on the job kind of thing. But if you have the right people, the right mentors to sit down and talk to you about that, it can be very helpful.
Yeah, absolutely. Mentors are key. I wouldn't be where I am without people along the way that have helped me. To anybody new, and even to your students, like, what would you recommend in the process of trying to find a mentor, and like what is it that worked for you in finding somebody that you liked and got along with?
Yeah, I mean, you want to, I've had mentors who, in my career and in my personal life, right? Some, they help me with a certain aspect of something. Hey, I really like the way this person comports themselves. Yeah, their style in meetings, the way they talk to people. Or I really like their technical acumen. I've run into people at conferences over the years, and I like the work they're putting out. Or the way they go about their business. And so there's mentors kind of at distance, right, where you'd say, I can see what they're doing, I want to try and bring some of that into my own life. And then there's personal mentors, my thesis advisor, my first boss, who you want people who recognize the things you're doing, right, and both understand and appreciate, even if they sometimes want to push you on the right path.
Yeah.
So I think it's important to align with the way they're supporting themselves, the way they're doing business. But you want to feel recognized for what you're doing in not so much as in validation, but in the sense that I'm doing the things I need to do, and everyone wants to be told that, hey, I think you're going about this the right way. I think you're doing good work, and here's how to maybe do that better, or to have you thought about this, or the way you approach things.
Mm-hmm.
Hey, I see you have a great technical side. Maybe we need to work on some presentation skills, or hey, I really like this report you wrote, but maybe you need to change this up, or have you tried presenting it this way?
Yeah, somebody that's positive, that has constructive feedback, they'll prop you up a bit, but then say, let's tweak this thing, right?
Yeah, I mean, you want honest feedback, but also sometimes kind feedback is nice.
That's a good way to put it. Yeah. Absolutely.
I don't mind being told that, hey, that this wasn't quite correct. I liked this bit about it, but maybe we need to tweak this, right?
Yeah.
And that goes for mentors too. Brutal honesty isn't always the best thing, right?
Yeah.
I listened to your welding episode, and I think we've all had bosses like that in some way, and the tough love and that you can kind of experience in the trades is it's certainly one way to do it. Whether it's the best or not. I mean, I worked in a machine shop for a couple summers, so I
all about it.
I definitely understand. And it's a little bit, it can be a little bit different, and recognizing the different ways to be a mentor is important, and for people mentoring newer people below them.
Yeah.
Offering support in some way or another.
Yeah, absolutely. Well, I mean, you gravitate towards the people that are like you, right? And that's just the way it goes. Not everybody's going to get along. But I would also say, if you're mentoring somebody like yourself, that's part of your process too, right? Like you're learning more about your craft and trade and knowledge just as much as they are, right? Because you're learning how to teach it, which is so hard to do.
Yeah, we talked about communication at the beginning of the episode, right? Reaching the people, right? A good teacher knows what avenues to take to reach someone, and that it's not the same for everybody.
No.
I may be mentoring two people, and one person requires a little bit more pressure, a little bit more motivation, and the other person may be better off with little hands-on support, but a meeting every once in a while, or hey, that was good,
yeah,
it was a good job, keep it up.
Yep.
Everyone requires in different ways, and it's important to recognize those ways, right?
Yeah, absolutely, man. Cool. Well, I'm not going to take any more of your time, because you're probably got lots going on, and this is great, man. Thank you. I appreciate it.
Of course, I always enjoy our talks, Greg.
Yeah, man. And we're going to do it again.
Okay.
And yeah, until next time, thank you. And we'll be in touch.
That sounds great. Thanks, Greg.
Okay, man. You have a good weekend. All right.
You too.
Okay. Bye.
Bye.
Greg Sheldon here, your host of Metal, Steel, Manufacturing, and Business Pro podcast, where you learn everything about the metals and manufacturing industry that make your modern day life possible.